Okay, so we're going to take a look now at calculating the moment of inertia for extended bodies. Up to this point, we have the moment of inertia for a point particle is equal to m times r squared. And when you have an extended body, you can think of it as being made up of an infinite number of point particles. Well, it's obviously not practical to try to sum up, millions and millions of particles. And so what we're going to do is use calculus to determine what the moment of inertia is going to be. Our new moment of inertia equation is based off of this one and the summation of it. And we have I is equal to the integral of r squared dm. Now, in this particular example, we're going to determine the moment of inertia for a long thin rod, which you should know from last year that the moment of inertia for this rod is going to be equal to 1/12 ml squared. But before we do this, I want you to think about the limits of integration, all right, because this is a really important point. Whenever we use our moment of inertia equation, how do we select our limits of integration? So for this particular problem, just take a moment and think about it. What are the limits of integration going to be for this problem? Now hopefully you said that it's going to have to go from minus 1/2 L all the way to L. And that's because by definition, R is the position relative to the axis of rotation. So what that means is if I have this total length of L, if I go to the left of the axis of rotation, I'm going 1/2 that length. And when I go to the right, it's going to be equal to 1/2 that length. One is in the negative direction, the other is in the positive. So that's the thing that you have to be careful with when doing moment of inertia. Okay, so let's go ahead and set up and solve this integral for the long thin rod. So by definition, we have I is equal to the integral of r squared dm. Now, the critical step in solving these problems is always going to be converting this dm into a dx, a dA, or a dV. Okay, and of course that's where the mass densities that we've learned about come in to be really important. Okay, so in this case what we have is we know that lambda is equal to the mass per unit length when it's a uniform mass density, and that is of course what we have in this situation. So lambda is equal to mass per unit length, and in the limit, as our chunks get really small, we can write that as a dm dx. So if we're going to be getting rid of dm, we have to solve this for dx, and we get dm is equal to lambda dx. All right, so let's make our substitution, and we get I is equal to the integral of, now let's make this conversion right now. R is just a one-dimensional thing. In this problem, everything is horizontal, so we're just going to use an x instead of r. So we end up with x squared times lambda dx. All right, now lambda, remember, is also m over L, and so we can write this as the integral of x squared m over L dx. So that when we integrate this, remember we go from minus L over 2 to L over 2. So when we integrate this, we're going to get mx cubed over 3L evaluated from minus L over 2 to L over 2. Okay, so let's do that evaluation, and we're going to get I is equal to m times, now L over 2 cubed is going to be L cubed over 8. And this is going to be over 3L minus, and then we're going to do the same thing. That's going to give us an M times a minus L cubed over 8 divided by 3L. So now you can see that we're going to get some canceling. This L cancels with one of those L's. And whenever we simplify this fraction, we end up with the 8 going in the denominator. So we have I is equal to ml squared over 24 plus ml squared over 24, because this negative and this negative make it positive. And we have 2/24, which is the same thing as 1/12 ml squared. So we've actually shown what we set out to show, and that is at the moment of inertia for a long thin rod where the axis of rotation goes through the center of mass is going to be equal to 1/12 ml squared. Now, we've also learned last year that if I take this axis of rotation and I shift it from the center all the way out to the very end, so that now my axis of rotation is here, that moment of inertia should be equal to 1/3 ml squared. Now, what's particularly cool about doing this with the calculus method is that you don't have to use the parallel axis theorem to determine your moment of inertia. Now, don't get me wrong, parallel axis theorem is usually far easier if you already know what the moment of inertia through the center of mass is going to be. And we'll get to that in another video. But this is still kind of cool doing it the calculus way, because really what ends up happening is when you set the problem up, once you've gotten through that initial setup phase, the only thing that's changing are your limits of integration. Because you're moving your axis of rotation from the middle to the end, we can just jump in from this step right here. So I'll just start by writing I is equal to mx cubed over 3L, and I now set my limits of integration to go from 0 to L. I just have to make sure that I account for the entire rod. So this is going to go from 0 to L. And now I think it becomes very obvious that the moment of inertia here is going to be m times L cubed over 3L minus 0. And so we end up with I is equal to 1/3, because this is going to cancel, and that with that one. So that's 1/3 ml squared. All right, so it was very quick and easy to do this using the calculus method versus the parallel axis theorem, which is just a little bit more work. But suppose I wanted to put the axis of rotation right here, 1/4 of the distance from the end of the rod. Well, again, we can just write I is equal to mx cubed over 3L, and now we evaluate it from a minus 1/4 L to 3/4 L. All right, so that's the principle that I'm trying to demonstrate for you. So the calculus method, it can be easier. It just depends on your own personal skill set.